no more talking. Sorry, the recording. Where's everyone? Oh, what's up, guys? Why are you doing this fake soccer fan?
I'm gonna factor and then check.
Sure, do it.
No, I just have the solution and I say, oh, I guess with -2 good, so I'm like,
oh yeah, RRT means rational root theorem. In case you didn't figure it out.
Bruce, we have a shitty one, please.
Hey, you're on recording mode.
We are?
Oh, damn.
Yeah, they're having us record all the lectures.
Why?
Because if people are absent, then we should send them the recorded lecture.
That happened to us in geometry, but we ended up sending too much bad shit on it.
Huh?
Yeah, we did say it to get
It's
that
great.
time.
And in cam, we're right next to the microphone. Me, Deb.
You should whisper and be like,
You dead? Who else?
Shriyansh is there.
I don't know who that is.
Shriyansh? You know?
Didn't Deb like fall off a bike?
Yeah, he fell down with milk.
Sucks, dude.
The 1-for-1. Or 1 shoe.
Alright, guys, take more than these. Should take more than 3 or 4 minutes.
Still at my time.
You then use figure that represents all the solutions that are possible for this, or like that could be possible for this. And then we make this symbolic division.
wait, okay.
Like so, P over Q.
Wait, which are the people?
No, it's just that that's where.
Randomly some variables taken.
So P. Oh, thanks.
Alright, so no more copies. I just told him to print some, so.
Okay, so P would equal
We get some.
all the factors.
You don't really need a copy of this for today, though.
So those are the P down there.
Yeah. What's plus minus P plus minus 1 plus minus.
Oh, that?
Yeah. And it's over Q, which is all the factors of the coefficient of the function, which is nothing.
Zero? Zero?
1, 1. Okay, so it could be -2, -1, -1, -1, and so
For
you
the,
just start
for the dividend divisor? Denominator. Because the dividend.
I don't know, but
Oh, okay.
you can.
That is divided by. Which is not. Oh, dear. Thank you. Your sacrifice has been appreciated. What sacrifice? Your entire knowledge. This was a guessing checkers. How do I know if it's the right?
Because then the remainder would be 0 once you put it in the simple.
I wasn't sleeping last week.
Kind of work.
It's right there.
I was concentrating with my eyes closed. So my
You done? You done? How did you get that? How did you get the factory so quickly?
What do you mean?
How did you know which one to guess with?
Oh,
You cheated there, didn't you?
How?
You cheated.
It's efficiency.
It's not efficiency, you cheated.
It's efficiency. I can go back and look at the solutions.
You're joking, right?
Only like that's like Rusu says if she puts a method on the test, she actually gets really pissed off if you do it the faster way.
Yeah, because you're practicing the method. It makes no sense, right? It's just math is about efficiency and like getting to the answer quicker, but it's just also practice the method, right? It's like it's kind of a catch-22 situation. Like, I don't know what to do. I mean, you're supposed to be repeating probably, right? So like,
Yeah, no what
I mean, to be fair, if you understand synthetic division, then there's no point in
There's no
keeping testing, right? So it's fine, honestly. Keeping practice in synthetic division for some reason, but just practice testing. It's a good way to practice, right? So you can free copy.
I think so.
Honest free copy. So you get.
I might drop it. It's like I don't know. I'm still like thinking about the video because it's like if I do it now, then I'll get to like because I don't want to get a B though. That's the thing. I do want to get to.
It's fine to get a B, honestly. You mean junior or sophomore?
I'm going to sophomore.
Oh.
So then I was like, anyways, just.
It's fine.
I mean, it's just like I'm gonna have to do it again though.
I got a B first semester of honors free copy. I got an A.
Oh, then you have to do it.
But I took BC anyway.
Because I got an A in the second semester.
And BC like Peralta and stuff. Well, I got like a solid in Peralta.
I'm gonna ask.
I think Peralta's a lot easier than any other.
He is the first. I'm gonna ask to put math and science after lunch or math and chem. All every year. First midweek.
How do you do that?
You can ask them. Like you know Shreyas?
Aurora?
No, probably.
Oh, the guy that looks like Ishmael.
Esau. Yeah.
Alright, is everyone finishing up? He's in track, right?
Yeah. He kind of carried the 4x4 in the time.
Alright, guys. So we have a lot to do today. I'm sorry we don't have enough copies of this. You don't really need the lecture handout. I'll give you guys copies if you still want it on Friday or Saturday for you guys. But you don't really need it today. I'm just gonna talk about it, and you already know most of it. This is reviewed. So we're gonna first do this. This is what we talked about on Tuesday, right? We talked about the rational root theorem. So on Tuesday we went over, we reviewed long division, synthetic division, which are just ways to divide polynomials or find factoring methods. If you guys remember, if I'm gonna keep hammering this into you. If you have a remainder of 0, what does that mean? If you do long division, synthetic division, if you divide something, you get a remainder of 0, what does that mean? It's a what? It's a factor, right? So that's why synthetic division and long division are good ways to check if something's a factor of a polynomial. If you simply divide and you get a remainder of 0, then you know it's a factor, right? And you guys remember how to like read off the coefficients to figure out the polynomial? Everyone understands that? So no one wants me to review like long division or synthetic division or anything? We're all good? Okay. So then we went and talked about factoring polynomials and then solving polynomial equations by factoring. One of the ways to factor is using the rational root theorem. So this is why I did the warm-up. All right. Is that ringing? That's so weird. I don't know who's calling on that. All right, I'm gonna erase the first. So here, we're gonna first list out the factors of negative, it's not negative 4, positive 4. So we're gonna do plus or minus what? 1, 2, and 4. Those are the factors of 4, right? And then we're dividing by the leading coefficient, the factors of that, and that's just a 1, right? This is a 1 there. So this is a plus or minus 1. So we're gonna have to test out plus or minus 1, 2, and 4. Now, I was talking to AJ about this. So your teachers are gonna make you like actually show all your work when you're testing stuff out. But for the sake of time right now, you can look at this and just see that this is easily factorable. So you know the answer already. If you can see this as x squared times x plus 2 plus 2 times x plus 2, like that. Right, you can just factor into that by grouping. Then you know you need to test out -2, right? -2 is what's going to work because that's what's factored out. So for the sake of time, we're going to skip over and be like, oh, we found already. Like on our first try, we got -2. So So if we do negative 2, we have 1, 2, 2, 4, 1, 0, 0, 2, minus 4. So we notice that, oh, negative 2 worked. So that means that the first expression will be x plus 2. Everyone understands why if negative 2 is our root, then everyone understands why this has to be x plus 2, right? Because when we set this equal to 0, we'll get x equals negative 2, which is what we solve for, right? And then we just read off the polynomial coefficients from here. So this is going to be x squared plus 0x plus 2, which is also x squared plus 2. And this is going to be equal to 0. And then we'll get, I'm going to erase this. Then we'll get we'll get one real root, which is x equals negative 2, right? And then the other one is, so x is equal to plus or minus root 2 I. So, question number 1, does this satisfy the fundamental theorem of algebra? Why does it satisfy the fundamental theorem of algebra? Yeah.
There's 3 solutions and like leading lengths 3.
Yeah, exactly. So there's the degree is 3, right? And the fundamental theorem of algebra says that the total number of roots of a polynomial equation of degree n, in this case degree 3, has to be n roots, right? So the number of real roots plus the number of complex roots has to equal 3. So we have one real root and then 2 complex roots plus or minus root 2I. So that's 3 total roots. Any questions on this, guys? All right, so I skipped over all of the testing of possible roots because you know, you can easily, not easily, but you can like tell like root factoring by grouping what it's going to be. So here, like I'm fine if you can do that on a test, but like or a quiz or whatever. Remember in school, like your teachers are going to make you like they're not going to like it. Like AJ said in Rusu, she wouldn't like it if you factor something in a more simpler method instead of using the rational root theorem. So make sure you guys are kind of like actually using the method that your teacher asked for, right? Like I personally am fine if you can like find it and then use, because I know you guys know how to do synthetic division. So I'm fine if you like find the factor first and then just like test it out and make sure it's remainder 0. But make sure in school you guys don't do that. Unless your teacher says something else, but most teachers will like not like that, so. Any questions? Yes? Alright. Alright, number 2. Shoot, I erased it already. What is number 2? Anyone? You have number 2 down? Huh? Get number 2 there.
4x cubed plus x squared minus 4x.
Oh, yeah, okay. So we're going to test out plus or minus 1 over plus or minus 1, 2, 4. So again here, you can look at this and be like, that's easily factorable. This can be factored into, if you take out an x squared from here, you'll get 4x plus 1. And then if you take out a negative 1 from here, you get 4x plus 1. So then you notice that you can test out negative 1/4, that should work, or if you test out positive 1 or negative 1, because then you can factor this into x squared minus 1 times 4x plus 1. So let's just try out negative 1/4. So let's do 4, 1 minus 4 minus 1. So we get 4, negative 1, 0, 0, negative 4, 1, 0. And that works. So our first term is going to be x plus 1/4 times 4x squared minus 4. So then from here we'll get x equals negative 1/4. And then this one, 4x squared minus 4 equals 0. We can just divide this whole thing by 4, so we'll get x squared minus 1 equals 0. So x is equal to plus or minus 1. So we have, in this case, 3 real roots, negative 1/4 and then plus or minus 1. And that does satisfy, as we know, the fundamental theorem of algebra, because there's 3 real roots, which matches the degree n, which is 3. Any questions on this, guys? Everyone's good with the rational group theorem? So it's going to be pretty applicable in a lot of like, so when we're doing like applications of all these things, if you're like solving, polynomial equations are going to come up a lot, right? In algebra 2, pre-calc, calc. If you need to solve for a zero and you can't factor, you can't use a quadratic formula if it's a quadratic, if it's not a quadratic, then this is what you're going to use, right? To solve it by hand. Obviously, in real world, like after college and after you're done with all your math classes, you won't need this, right? You're just going to plug it into a calculator and figure everything out. But this kind of helps you understand why the zeros you're getting on that calculator. This is how the calculators are programmed. They use like a tracing feature on your graph. So like they approximate the point. I don't know if your teachers have shown you. Maybe I'll show you at the end of this entire like thing how the graphing calculator works, because it's nice to know for algebra 2 how to use your graphing calculator. So, all right, any questions on this? So today we're going to be doing the very last part of chapter 4. Chapter 4 is about, again, polynomials. So we're going to cover the graphs today. I talked a little bit already about it. We talked about like x cubed, x to the fourth, like some parent functions like that. And then we talked about like in general what those functions will look like. So we'll go over that again today, and then we're going to go over also some principles, some theorems, or how to analyze graphs basically. These are things that you haven't learned actually. So in Algebra 1, you covered graphing from a very broad perspective, but today we're actually going to talk about, like within graphs, like specifically how to look at, how to identify like a zero and approximate turning points, things like that. And then maybe help you guys like sketch graphs a little bit quicker. So, so on your lecture handout, if you have one, you don't really need it, but I'm just going to talk about some steps that will help you graph polynomials. So, number one, if you can factor the function, like a very common thing is, I don't know if you guys can read that. That says x squared plus 4x plus 4 equals 0. So f of x equals this, and you're asked to graph this quadratic function here. You could sit here and like try to find the vertex, all that stuff, but you can simplify this, right? You can factor this into x plus 2 squared, and then because you guys are really good at transformations, you'll see that, oh, this is just a translation to 2 units left from x squared. And that makes it a whole lot easier to graph. So in some cases, factoring would be easier. Sometimes it's not, right? Like sometimes it might confuse you, and then you won't be able to tell exactly where the y-intercept is or something. So pick your chance, like kind of when to factor. In quadratics, it's usually easier. Even with cubic functions, but sometimes it might not be. Okay. Second one is determine the domain and range to give you an idea of the shape. So in this case, the domain is all real numbers. For quadratics, it's always all real numbers. And the range is going to be y is greater than or equal to 0. But that might change, right? If you translated this guy up or down, the range is going to change. Domain would never change, but range might change. So that would give you an idea of like where the graph is going to be on the plane and things like that. Number 3 is to find the x and y intercepts. That's pretty common sense. You always, for every function, you're going to try to find the x and y intercepts because it's going to give you a good idea of where the graph across the x-axis, y-axis. Number 4 is to find the multiplicity of each zero. Do you guys remember multiplicity? So if the multiplicity is even, what does that mean for the 0? Anyone knows? Yeah.
The 0 is the vertex?
Yeah, so it's a vertex. I'm trying to think more like a broader perspective. So it means that it's going to bounce off. So yeah, it is a vertex because it's going to bounce off. So it's going to be the minimum point or the maximum point. But in more general terms, it just means it's going to bounce off. Like the graph is going to bounce off of that 0. In this case, right, -2 has a multiplicity of 2, right, because it's being squared. So when you look at the graph of this, it's going to bounce off of -2. What if the multiplicity is odd? What does that mean for the 0? Yeah, it goes right through. So if this was an x plus 2 cubed, that means that the graph is going to go right through -2. Like that. Make sense? Alright. Because this is a cube, so it's a multiplicity of 3. So multiplicity will give you an idea of like what's happening at the x-intercept. Is it balancing? Is it going through? Find the vertex if applicable. We'll talk about actually square root functions today, which you guys learned last year, I think. Radical functions. So in there, finding the vertex is useful. Quadratics, obviously, finding the vertex would be useful. Finding the absolute minimum or maximum. And then if none of those work, you can always like plot different points. Just plug in x into the function, like some random x value, get a y value, and you'll be able to tell like from there. But hopefully it doesn't come to that. It's going to be a lot easier instead of like having to grind out numbers by plugging it into the function. It's going to be a lot easier to like do these other different things that are a bit easy. Any questions on graphing? We're going to talk about some functions today, which I think we've talked about before a little bit, but this will be more in depth. So x cubed, or actually we'll start with x. So x we know looks like this, right? This is a line. X squared, quadratic, looks like this. And then x cubed. X cubed is not going to be obviously a straight line, right? It's not linear, but it's going to look pretty similar. So it's going to start in the third quadrant. It's going to work its way up through the origin and back up like that. So it's kind of like a snake, right? It just starts here, goes to the origin, goes back into the first quadrant. Very similar to a line, except as you can see, it grows a lot quicker than a line because x cubed. If you plug in some value of x into x cubed, it's going to be a lot bigger than plugging in that same value into x, right? Like 2 cubed is 8, but for on the line y goes x, 2 is equal to 2, right? And it's going to decrease a lot quicker too, like negative 2 cubed is negative 8, but negative 2 on the line y goes x is negative 2, so you see why it's going to grow a lot quicker there, or decrease a lot quicker. X to the fourth looks like this. So you see that it's been a bit compressed, and the reason for that is it's kind of like a vertical stretch. So this graph here, we know that like if you plug in x equals 2, so if you have like, say this is, so in this one, right, say x is equal to 1, then y equals 1. If x equals 1 here, y equals 1. Sorry. Right, so at 1, they're the same. But notice that at x equals 2, y equals 4 here. And for x to the fourth, if x equals 2, y is equal to 16. You notice how big of a jump there that I made there? So that's why this graph here just rises up a lot quicker than, x to the fourth rises up a lot quicker than x squared, right? Because when as your x increases, your y is increasing at a much faster rate. What if x is equal to 1/2? What would y equal to for x squared? Yeah. 1/4. 1/4. And then in this case, y is equal to 1/16. You notice how 1/16 is a lot smaller than 1/4, right? That's why this graph here, it's going to get really flat towards the origin. X to the fourth gets really flat because it gets closer and closer to 0. And it gets closer and closer to 0 a lot quicker than x squared does. It has to flatten out to get closer and closer to x squared, and then at x equals 1, it goes off after that. Make sense, guys? So that's x to the fourth. So a general kind of rule here is that anything with an odd power, so like x to the power 1, which is a line, x cubed, x to the fifth, is going to look something like this shape here. And then anything with an even power, so a quadratic, quartic, sixth power, etc., is going to look like a quadratic function. But we know, like, you know, x to the power of like 100 is going to look something like this. It's kind of cool, actually. It's going to look a lot like that. It's going to look almost like it's hugging the y-axis, because after x equals 1 and x equals 2, 2 to the power of 100 is enormous, right? So at some point, like, this graph has to get really, really big. So it's going to look almost like it's hugging the y-axis. You're not going to be able to even see it if you go from if you like zoom out on a graph like on Desmos, you won't be able to even see x to the 100. It'll look like just the y-axis. Make sense, guys? Everyone understands it? This is just like a in my opinion at least, like analyzing graphs and like understanding it's pretty good. It's pretty useful. You understand functions better. You understand like why the function is acting like it is. We're gonna go over next week something called end behavior. End behavior just means like as x approaches positive or negative infinity, what's happening to the function. So we'll go over more of that next week because functions will be dealing with kind of it's more incorporated into that. This is pretty obvious. Those it's not as obvious. So okay. So the last part of chapter 4 deals with a few new things, some old things, a few new things. So who here remembers even and odd functions? We were kind of? Okay, we'll go over all this today. We're going to do a lot of practice for it. So the idea behind even and odd functions is that we're testing out, so if you have a function f of x equals something, some function, if you test it out f of negative x, meaning you plugged in this is a bad marker, sorry. You plugged in a negative x for every x value into the original function. So you plugged in, say it was x squared, so f of negative x would be negative x squared. You're just replacing every x with a negative x. You're trying to see what f of negative x is equal to. F of negative x is equal to, in this case, it's equal to x squared, which is the same as our original function, so it's equal to f of x, right? If f of negative x is equal to f of x, this is called even. It's an even function. Right? Are you guys starting to recall this now? So again, if f of negative x is equal to the original function, which is f of x, right? Negative x squared is just x squared, right? Because no matter what, if you're taking some negative, so this is what? Negative 1 squared times x squared, which is x squared. Everyone understands that? Say that, now let's say that f of x was equal to, x cubed. Now, f of negative x is going to be equal to negative x cubed. What is negative x cubed? Sorry, negative x whole cubed. What is that equal to?
Negative x cubed.
Do you guys see that this here is the same thing as negative 1 cubed times x cubed? Negative 1 cubed times x cubed, which is equal to negative x cubed. Which is equal to, in other words, negative f of x. Because f of x was equal to x cubed, so now this is equal to negative x cubed, which is negative f of x. And this is called an odd function. So I'm gonna write it in more general terms here. So again, if f of negative x equals negative f of x, it's odd, it's even. If f of negative x equals f of x, and then if f of negative x equals neither, then it's the same as neither. Any questions on this? We're going to do a few practice problems. I'm going to show you some examples and you guys will do a few just to make sure. Actually, before that, let me explain what this means. Are you guys done writing? Or? Okay, I'll wait a minute or two. I'll explain what this means graphically or geometrically. understood this, right? Like everyone understands the background, right? Even on functions. Alright, so everyone look up here real quick. You guys see, when we do f of negative x, does anyone know what kind of transformation this is? If we were doing negative x, yeah. What kind of a reflection? Think about if you're swapping your x coordinates, right? So if you have like a function here that looks like this, if all your x coordinates are becoming negative, it's getting, yeah.
A reflection across the y-axis.
Across the y-axis, right? Because all your x coordinates that are positive are becoming negative. So this graph is going to be flipped over here. So it's a reflection over the y-axis. So if a function is odd, that means that a reflection over the y-axis means that it's the same thing as a reflection over the x-axis. Because if f of negative x equals to negative f of x, negative f of x is a reflection over the x-axis, right? Because you're swapping your y coordinates here, right? F of x are your y coordinates, and negative of that, you're swapping over the x-axis. Or you're flipping over the x-axis. Make sense? So if it's an odd function, that means that a reflection over the y-axis is the same thing as a reflection over the x-axis for that function. So a good example is a line. So y equals x looks like this. If you had f of negative x, so just y equals negative x, a reflection over the y-axis is the same thing as a reflection on the x-axis, right? So this is y equals negative x. You notice that if you took y equals x and reflected it over the y-axis, you would get this line here. And if you took y equals x and reflected it over the x-axis, you would also get this function. So you notice that in an odd function, the reflections are going to get you the same graph or same function. Okay? Does that make sense? Did everyone understand that? All right. How about for even functions? Does anyone want to try to explain using the same logic that I showed you here? Would someone want to try to explain what an even function would be then? Anyone?
It's just flipped over the y-axis.
Yeah.
So it's like
Exactly. So a good example. So I'll say what he said again. AJ just said that it's a flip over the y-axis. So because f of negative x is a reflection over the y-axis, if f of negative x equals f of x, that means that it's symmetrical across the y-axis. So a good example is x squared. You notice how x squared is symmetrical across the y-axis, because if you take any x coordinate over here, like 1, 2, 3, etc., and you made it negative, you would get the same y value, right? Because 1 squared, 2 squared, 3 squared are the same thing as negative 1 squared, negative 2 squared, negative 3 squared, respectively, right? So you notice that it's symmetrical across the y-axis, so you're just reflecting this part of the graph, it's reflected over the y-axis. Everyone understands that? So that's what an even function will look like. So this has a few applications, not many in Algebra 2, at the Algebra 2 level, actually. The most that I can think of, at least, are just, like thinking about graphs in a better way. In calculus, though, you will see, like, in calculus, you'll learn how to find the area under a function, or under a curve. So you learn how to find, like, exact value of this area right here. And you'll notice that sometimes it's a bit easier to know, like, if you're asked to find the area from, like, this coordinate here to this coordinate here, you know that it's symmetrical because it's an even function, so you can just find this area and multiply by 2. I don't know if that made sense, but it is applicable, so make sure you do, like, remember this. It's something not to forget for sure. Any questions on this? So does anyone have an example, or can anyone come up with an example of a function that is neither even or odd? Because that is definitely possible, right? You can have a function that's neither even or odd. Anyone else? Come on, guys. All right. How about x squared plus x? Is that even or odd or neither? So f of x equals that. What is our first step to test whether it's even or odd? What do we have to do? F of what? F of negative x, good. Which is equal to negative x squared, which is this x squared, and then negative x. So you notice, now you have to figure out what is this function. Is f of negative x equal to f of x? Yes or no? No, right? It's not, they're not the same. Is f of negative x equal to negative f of x? No, right? Negative f of x is negative x squared minus x. This is not negative x squared minus x. This is x squared minus x. So they're not the same. So that's neither, right? Everyone see that? So a good way to approach this is to write out negative f of x maybe as well, so you can easily compare. So maybe just write out on top of f of x, write out negative f of x, so that when you have to like compare this f and negative x, you can see it pretty easily. Everyone understands this? Did you guys learn? No. What's up? Just keep teaching. Oh. So did you guys learn trigonometric functions yesterday? Not yesterday, last year? You guys did? Not you. People in Algebra 1, did you guys learn? Okay, so we're not going to go that. So we're going to do some practice of even and odd functions. Some non-trigonometric functions. So here you're just going to determine whether it's even, odd, or neither. I'm going to come up with a few. It's going to take more than a minute or 2 minutes. You wait though. I can usually tell. first one. Victor, is it even or odd?
Oh, it's an even.
Even, right? So, again, you got it right. So, the way to test it is that you set f of negative x, and you just plug it in. So, negative x to the power 8. And we know that any negative number to an even power is going to be the same thing, right? Like negative x squared, negative x to the 4th. And the reason, again, is that you can break negative x into negative 1 to the power 8 times x to the power 8. And we know negative 1 to any even power is going to be 1. Everyone knows that, right? Okay. So this is just going to be, it's even, good. So this is equal to f of x. Right? So we're equal to the original function. Number 2, Heidi?
Neither.
Huh?
I say
Neither. Okay, good. So again, negative x equals negative x to the 5th plus x squared. Because when we plug in negative x here, it's going to be a negative because it's an odd power. So we get negative x to the 5th plus x squared. Because again, negative x squared is just x squared, and that's neither the same as function or the negative of the function. So this is my and then the last one, Alicia. It's odd, yeah. So, did you guess, or did you like? So, g of negative x is equal to, again, you're doing negative of negative x to the 5th minus negative x cubed. What is negative x to the power 5? Yeah, it says x to the power 5. No, not it's negative x to the power 5. So negative x to the power 5 is negative x 5th. So negative becomes positive. And then same thing here, right? Negative x cubed is negative x cubed. So it's negative says positive. Everyone can see this, right? So our final g of negative x is x to the power 5 plus x cubed. And you guys notice that's the negative of g of x. If you take the negative of g of x, you'll get this. So that's odd, right? G of negative x equals negative g of x. It's odd. Everyone understands even and odd functions completely. Does anyone want any more practice on this? Everyone good? Good? Okay. Maybe what's next? Okay. So, two more things now. So, you guys remember, I don't know if you guys remember, but I told you guys the graph of x cubed plus x squared, right? It looks a bit like this. And I told you guys that you can't, with algebra knowledge, you guys can't find the exact values of these turning points. These are called turning points, right? You'll learn how to do that in calculus, but these two things here are called relative extrema. And you'll learn a lot more about this in calculus. So relative extrema, all this means is that these are not like the absolute maxima or minima, right? The absolute maxima is infinity. It doesn't really exist because this function increases or continues towards infinity, and this function here decreases until negative infinity. So you can't find like an absolute maximum or minimum per se. But these two, if you look at this y value right here, at this turning point, you'll notice that it's a relative extrema because on some certain interval, from like say this interval to like here, this here is the highest point on that interval. It's like thinking about like a mountain range, and then you're like within like a 30-mile span, that point is the highest. Same thing. But in the entire mountain range, it may not be the highest mountain, right? Same thing here, like this is the lowest point on a certain interval. So it's like if you're in a valley, This is not a great example, but yeah.
What if you have like more than one
So like, you're saying if it was like this, that?
Yeah.
So then this here is a relative maxima on another interval, like this interval right here.
So there's only one for one. So there's only one for one.
No, well actually, there's technically an infinite number of intervals, right? Like you can take, so this here, oh, this is a bad example. Let me draw this a bit bigger. Okay, it's a roller coaster. So this is the highest point on this function continued on the interval from negative infinity to like right here, right? This is the highest point. But this here is the highest point from negative infinity to like right there. Does that make sense? But you can find a bunch of intervals on which this is the highest point. Like this on this interval, from here to here, this is the highest point. From like here to here, that's the highest point. So that's why I'm saying there's an infinite number of intervals on which like these. That's why it's called a relative extrema. It's relative to that interval. It's not an absolute maxima, which means that it's not the maxima of the entire function's interval. It's only relative to that interval. Does that make sense? You sure? Does that make sense? Okay. Makes sense, guys? So, so that's just like a little bit of theory, but let me redraw the graph real quick. So this is x cubed plus x squared. So what's the degree of this function? It's just 3, right? N equals 3. So it's been proved that the number of turning points for a polynomial of degree n is equal to n minus 1. So you can see here there's 2 turning points, and that's because, again, a good way to remember this is that because of the fundamental theorem of algebra, we know that this function here has to have it has to have 3 roots, right? And those 3 roots, so each time you have to kind of pass through a root, it has to come back to meet the other root, right? So like, if you pass through 1, 0 over here, the function has to turn back towards the x-axis. So for every two x-intercepts, there has to be 1 turning point. Does that make sense? Which is why there has to be n minus 1 there. So n minus 1 turning points. Don't need much practice on this. I mean, this is pretty easy to visualize. All right, and the last part of chapter 4 we're going to talk about is something called the location principle. So all that the location principle says is that if you had some, so say A was over here, so f of A will be down here, right? So f of A. If f of A is negative, and let's say there's a B, this is f of B. If f of A is negative and f of B is positive, then between A and B, there must be at least one x-intercept. So that just means that, given that the function doesn't have any like asymptotes or something in between. So that just means that if the function is like continuing, like it doesn't stop for asymptotes or poles or anything like that. You guys will learn about asymptotes and poles, right? So if it doesn't stop for asymptotes or poles, then it has to cross through the x-axis because it goes from negative to positive. So it's pretty common sense that the function has to cross the x-axis. So I think you guys will learn about this in pre-calc a little more. It's called the intermediate value theorem. It's the same idea. Basically, there has to exist a 0 on an interval a to b, given f of a is less than 0 and f of b is greater than 0. Make sense? Pretty common sense, right? Obviously, if you had a rational function, this is 1 over x. this here is an asymptote, right? The y-axis is an asymptote. And here, say this is A, f of A is negative, and f of B is positive. But there are no x-intercepts, but that's because there's an asymptote, right? So you always have to check and make sure there's no like asymptotes or holes or anything like that. You'll learn about the more formal definition of this in calc. It's called continuity. The continuity of a function is just like you're making sure that in algebraic terms, you're making sure that there's no asymptotes, no holes, or anything that's going to like block the function, right? Make sense? That was the last part of chapter 4. So chapter 4 was a mix of like old and new material. Chapter 5 is I don't think it's much new to you guys actually. You guys have all learned about radical functions like square roots, cube roots from last year. Remember all that? So it's not that new. Yeah, it's not that new. It's gonna be a pretty good refresher. And then chapter 6 though is where it's gonna be like a lot of new material. So we're gonna finish chapter 5 in a few days. It shouldn't take that long. It's just like a review of square roots, stuff like that. And then we'll talk about logarithms, trig will be a lot of work, sequences and series and stuff. So, any questions though? Everyone's comfortable with chapter 4? Okay. So, we're going to be talking about exponents to start with. So, first of all, I want to make a distinction. X cubed is a cubic function, right? This is cubic. Someone yesterday in the other section said that this is an exponential function. This is an exponential function. When the variable x is in your exponent, then it's an exponential function. This is not an exponential function. That's very important. Please don't call this an exponential function. All right. So we're going to talk about exponents, properties of exponents, stuff like that. So the first one, you guys know that a to the power of 1 over n, or let's call it x. This will be easier. If you raise some number x to the power of 1 over n, that's the same thing as saying the nth root of x. Right? So like x to the 1/2 is just equal to the square root of x. X to the 1/3 equals cube root of x, etc. Right? Again, nth root of x, all you're saying is like, it's the opposite of taking x to the nth power. You're figuring out what's the nth root of x. So what number is being multiplied n times to get x? So in this case, like 49 to the power of half, you're like, what number is being squared, right? N. What number is being squared to get 49? That's a 7. If you raise x to the power of m over n, m is some other number, so m over n, you can rewrite this as, everyone knows this, right? From your properties of exponents, this is a power to power property, so this is the same thing as x to the power of 1 over n to the power of m, and then what's this equal to?
The nth root of x to the power m.
Yeah. So a good example is x to the power of 3/2. That's just going to be square root of x cubed, right? X to the power of half cubed, which is square root of x cubed. Make sense, guys? Any questions? This is especially useful for like, if you're asked like 4 to the power of 3 over 2, you're just like looking at that, you're like, I don't know how to do this. Then you can simplify it to the square root of 4 cubed, which is just root 4, which is 2, cubed is 8, right? Okay, some properties, other ones, x to the power of like negative a. So a negative exponent just means that you're taking into the denominators, it's going to be 1 over x to the a. These are the same things, right? X to the power of negative 2 is 1 over x squared, etc. Power of a power, I just talked about, like x to the power of m to the power of n is going to be equal to x to the power of m n. So you're just multiplying them together. So like x cubed and the whole thing squared is going to be x to the power 6, right? Because you're doing x cubed times x cubed. You're doing it twice. Make sense, guys? Good? And then a few more things. If you have the same base, in this case x, they're the same base, right? If you have the same base and you multiply two exponents together, you can then say this is x is 6 plus 2. Just combine the exponents, you add them together, so you get x to the power 8. Wow, I didn't write it up this already. Good. And then, same thing. Right, quotient x to the power 6 over x to the power 2 is equal to x to the power 4. A pretty important one is this one here. So a over b squared equals a squared over b squared, right? You just distribute the power everywhere. You can go backwards. Sometimes it might be useful to go backwards, so just make sure you do that. Same thing here, ab squared equals a squared b squared, right? Good? Everyone's good with these properties? No questions at all? Last one, anything to the power of 0 is equal to what?
1.
Okay. Good. That was a pretty rapid review of exponential properties. So we're going to talk about radical functions. Radical functions are any nth root functions. So anything with the form nth root of x. So the most basic one is the square root of x. This is the parent function of the square root family, right? So I'm going to talk about like some algebraic definition of root x, and I will talk about like what it means graphically. So you guys remember how to find the inverse of a function? Who here remembers how to find the inverse of a function? Kind of? Do you remember what you do to find the inverse? Yeah. So let's do that for, if you had say y equals x squared, the quadratic function. If you want to find the inverse of this, we're just going to swap x and y. So it becomes x equals y squared, and you got to solve for y. So y equals plus or minus root x. So what does this look like? Well, this is going to be a sideways parabola. You guys remember we talked about horizontal parabolas? Same thing. This is x equals y squared, right? Sideways parabola. But this is not a function, right? It doesn't pass the vertical line test. So in math, we've just restricted, the reason is that we've restricted this to just positive root x to make it a function. And that's why, actually, the shape of the graph of root x, this is positive root x. That's why it looks like that. Because again, this is just a sideways parabola. It's been shifted, it's been rotated. The quadratic has been rotated 90 degrees to the right. Make sense, guys? Obviously, if you wanted to check this, you could test points like 1, 1, 4, 2, 9, 3, and you notice that x is increasing a lot quicker than y, right? So that's why the graph is kind of flattening out after a while. Like x has to become really, really big. Like when x is 100, y is still going to be 10. When x is 625, y is still going to be 25. So you guys notice how much slower y is increasing than x is. So that's why the graph is going to like flatten out a lot. It's going to rise really quickly because like, just because, and then it's going to flatten out. Any questions, guys? So I don't think your book says this, but a good way to think about the transformations on a graph, of a square root graph especially, you think about this as a vertex. So think about this point over here where the graph starts, right? The graph's going to start over here, and it's going to go that way. Think about that point as h, k. So in this case, this is 0, 0. But if you could transform this, like, if you have root x minus 2 plus 1, it would just be moved over 2 units and up 1 unit. So this look like that. Right? Can someone tell me the domain and range of square root of x? Someone else, please? Just look at the graph. Ignore this guy.
The rate is x is greater than or equal to 0.
Uh-huh.
And range is y is greater than or equal to 0.
Right. Everyone understands this? So, the reason why, well, we all know why x has to be greater than or equal to 0, right? We can't take the square root of a negative number. But the reason why the range has to be greater than or equal to 0, think about, so when you had the square root of 49, you could say this is equal to plus or minus 7, right? Because negative 7 squared is 49, technically 7 squared is also 49. So this is equal to plus or minus 7. But that would mean that when you graph it, you would have to account for both positive root x and negative root x. So you have to account for this part of the graph too. Which is why, and in math, like we said, this is not a function. So to make it a function, we've taken out the negative, so we've restricted the range of the function. Everyone sees how we restricted the range, right? And why we restricted the range? So that's why the range is y is greater than 0. Another interesting thing is, and I was telling the other section yesterday, is when you're asked to find the inverse of y equals x squared, and you're not given any restrictions, you can't find this, because the inverse of y equals x squared is going to be y equals plus or minus root x, which is not a function, right? It's a horizontal parabola, which is not a function. So, because the inverse by definition has to be a function, so when you're asked to find the inverse of y equals x squared, you have to be given a restriction. You have to be given the restriction that x is greater than or equal to 0, or less than or equal to 0 or something. You have to be given a restriction on the domain, because remember from the inverse, the domain of the original function becomes the range of the inverse, right? Remember how they're flipped? So, you notice how the range has been restricted? That means the domain of the original function has to be restricted. So, the range will now be positive. If this was like this, then the inverse would equal to negative root x, because we've restricted the domain. So now the range has to be the same as the domain was of the original function, so it's been flipped. So that's why it would be negative root x in this case. Does that make sense? Yes? All right. So we did all this. Same transformations apply. Like if you did 2 times root x, it would just be a stretch. So it would be like that. A bit of a stretch. Half root x compressed. That. What about? This is a bit interesting. So we know what root x looks like. What about negative root x? What does that mean again? This is a what kind of transformation? What kind of a transformation is it? It's a reflection over the. So root x, these are the y coordinates, right? Because this is a function. F of x equals root x. Those are your y coordinates. So you're taking the negative of all your y coordinates. So it's x-axis, right? So you're reflecting with x-axis. So when you reflect this sort of x-axis, you're just getting this. So this is a so this is going to be positive root x. And you notice how this makes up that horizontal parabola, right? So this is just the other half of that horizontal parabola. Does that make sense, guys? Okay. What about the square root of negative x? How do we graph that? It is graphable, definitely. Anyone know? Anyone want to take a guess? I'll give you a hint. Try plugging in different numbers. Plug in like -4, plug in +4, and see what happens. And then see if you can figure out the restrictions. Yeah?
Isn't there a reflection over the y-axis?
Yeah. So you notice how all the x coordinates have become negative, so you're just reflecting over the y-axis. And that also means that, and a good way to think about it is that if you plug in any negative number here, plug in like -4. You'll get negative of -4, which is +4. So you'll have an answer there. So you know now, because the reflection over the y-axis, it's going to look like that. We'll have a new domain, right? The domain will be x is less than or equal to 0. Because all of these numbers, x has to be negative in order for the part inside to be positive. Like negative of -9 is square root of +9, which we can compute. But if x is positive, like if x is 9, we'll have square root of -9, and that we can't compute for the real plane. Imaginary plane, yeah, and we don't know how to graph like functions in the math. Even I don't know how to do that. I don't know when I'm going to learn that, but we don't know how to graph functions in the complex plane yet. We know how to graph in the real plane, but function in the complex plane, no clue. So, makes sense? We know how to graph points, right? We know how to graph like 3 + 2i, but those are just points. Functions, who knows? Makes sense, guys? All right. Let's do a few practice for this. Graph. This is do 2. Nothing too hard. That's a square root of -x, by the way. -x + 3. We have one more thing to go through, so we need to finish this real quick. Anyone want to come up and graph it? Try graphing this one. It's not too hard. Anyone? Alright, that's fine. So 2 times root x minus 6 plus 1. Where's the vertex going to be? Can someone tell me? The vertex, yeah.
6, 1.
Yeah, 6, 1. So it's going to be here. And then it's going to be, so you don't need to graph it exactly, just sketch it. It's going to be a bit stretch. It's going to start off pretty quick. Right? Makes sense, guys? The other one was root, what is it? Negative x plus 1 or something? 3? Okay. So root negative x is going to be on this side. It's going to be flipped over the y-axis and just moving it up 3 units. So something like that. Domain and range. What's the domain of this function? Yeah.
X is greater than or equal to 6.
Good. And then the range? Victor?
Y is greater than or equal to 1.
Yeah. And you can tell that just by the vertex, right? The vertex, like I said, is the starting point. It's just like a quadratic function. So this vertex is going to be the leftmost point, or in this case, the rightmost point of the graph. So it's going to tell us the domain and the range. But the rightmost point and the bottom point, or the top point, whatever. What's the domain here?
X is less than or equal to 0.
Range? Someone has it. Yeah, you agree.
Y is greater than or equal to 3.
Good. Make sense, guys? Okay, let's go quickly now. So the other type of radical function there is, well, there's obviously an infinite number, but the other type that we'll be kind of going over is the cube root of x. So everyone knows that the cube root of x is simply the inverse of x cubed, right? These two are inverses of each other. And a good way to think about it is that they're inverse operations, right? Like, if you're to solve x cubed equals 27, you would take the cube root of both sides. So you get x equals 3, right? So these are inverse operations, so they're actually the inverse of each other. So we know x cubed looks like that. So we know that just like y equals x squared, to find the inverse kind of graphically, we just have to rotate it to the side, and it's going to look like this. So x cubed, let me draw it in blue. So like that. That's cube root of x, this is x cubed. Same transformations apply. We're not going to go over it too much. You guys already know transformations. If I did cube root of x minus 2, it's just 2 units to the right. If I do a plus 1, it'd be moved up by 1 unit. Same idea, right? Everyone understands cube root of x? Domain range, all real numbers for both, because you can take the cube of anything, or sorry, you can take the cube root of anything, and then you can also cube anything. So there's no restriction on the domain or range. If you want to understand why exactly it looks like this, you can plug in points and you'll see why. But a good example, or a good way to think about it is that x cubed and x cube root of x are inverses of each other. So it's going to be rotated. We know, like, graphically, that means that if you drew y equals x, which is this dashed line here, then we know that to find the inverse graphically, we just rotate it over that line, right? You guys remember that from last year? What it means? Okay. All right, so last 10 minutes, we're going to talk about solving radical equations. Nothing too hard. We're going to do 3 types. I mean, you don't have to memorize. This is not something to memorize. It's just like different types of things you might encounter. So, for example, let's do this one. I think this one is in your lecture handout. 2 times the square root of x plus 1 equals 4. Very simple, right? What we're going to do here is we're going to isolate the square root. So we just divide the whole thing by 2. And then to get rid of the square root, we do the inverse operation, which is a squaring, right? we square both sides. So x equals root. Pretty easy, right? So these are obviously the easiest problems when you're just given like square root of something equals something. Just square it, get rid of the square root, solve it. How about this? Let me think about this one actually. Oh, no. There we go, okay. The square root of x plus 6 is equal to the square root of 2x plus 7. How do we solve this? Anyone guess how to solve this? Yeah.
You square both sides.
Yeah, you square both sides, so you get x plus 6. Wait. Hold on. I gave you guys the wrong example, sorry. Let me think about this real quick. I'm trying to think of a specific scenario, so I need to get an example for that. All right. Sure, this works. Yeah. So, like, wait, are you Sarah or Anna?
Oh, yeah.
You're Anna. Okay, so like Anna said, just square both sides, right? Get rid of the square root. So we get x minus 1 equals 2x, and then you just solve, right? So you get x equals negative 1. Final answer, right? Any disputations? Yeah.
It doesn't fit the domain.
Yeah, so a bit of a issue here, right? We got x equals negative 1, but you gotta go check back into the square root. Does negative 1 work?
It's 1, not negative 1.
Huh?
It's 1, not negative.
Why is it 1?
Well, I'm stupid.
So x equals negative 1, plug it back in here, you'll get square root of negative 2 is equal to the square root of negative 2. We're only dealing with real numbers here, and so this doesn't really work, right? So we've got to restrict this. We say, we solve for this, we don't box it exactly, so we just say x is equal to negative 1, and then we say no, because negative, just write like negative square root. This is called, does anyone remember from last year what this is called? What kind of solution it's called? Extraneous solution. And remember that from last year? So an extraneous solution, typically it comes when you, so here, right? You have the square root. There's a restriction on the domain, but when you square both sides, you're getting rid of that restriction on the domain, right? Because when you have a square root function, you remember a square root function looks like that. The domain is x is greater than or equal to 0. When you square the square root function, you'll get this. There's no restriction on the domain of x squared. Oh, sorry, you won't get that, you get this. When you square root x, you get a line, looks like that. There's no restriction on x. Square root of x squared is just x. There's no restriction on the domain of x, which is why we can solve for x. But then we have to go back and check the original problem and see that, oh, there's a restriction because it's a square root. Everyone understands why we got the solution, right? The solution happens because we squared it, so we're not worried about the domain after a while. So we gotta check, and then we say no extraneous solution. Make sense, guys? Okay. So the last problem we'll do, let's do something. So So here, square root of x minus 1 and then plus 2 on the outside equal to the square root of x plus 1. First step, we're just going to square both sides. So if you square both sides, you'll get x minus 1 plus 4 root x minus 1 plus 4 equals x plus 1. Right, you just FOIL this out. So it'll be this squared plus 2 times AB, so 2 times root x minus 1, which is 4 root x minus 1, plus b squared, which is 4. So x is actually canceled. And then if we move all the variables on that side, we get 2 much, so we get 4 times root x minus 1 is equal to, if you add 1 and subtract 4, we get negative 2. So then root x minus 1 equals negative 1/2. Is that possible though? Can the square root of something be negative? No, so actually there's no solution to this. And the reason is, like I showed you on the graph, square root of x is only defined for y is greater than or equal to 0. Right? So that means that the square root of something cannot be negative. Like you can't see a negative square root on the graph, right? It's only greater than or equal to 0. So no solution in this case. Make sense, guys? That's it for today. Sorry, no copies of homework. I will send it out by email though. I promise. I kind of forgot to do that last time, but.